chapters 12, 13, and 19. I'll point out, assume it's 12 and 19 unless I say otherwise. I'll point out when we're doing 13 stuff. Sorry. So. The other problem being a little late. How many units of unsaturation in that molecule? Three. So that's 122 flashback. If you're not familiar with that term, a unit of unsaturation is just, so right, we call them saturated hydrocarbons if you've got as much hydrogen on the molecule as it can take. So right, 6 carbon hydrocarbon can have 14 hydrogens. So C6H14 is saturated. If I pull 2 hydrogens out, I've created an unsaturation. So an unsaturation is either a pi bond or a ring. 3 pi bonds, 3 unsaturations. Predict that product. Predict that product. A whole bunch of products for you to predict. Okay, so hopefully you have a few of those at this point. Basically, this is a question about selectivity, and that the more reactions you learn, the more important this question is going to be, right? So I don't know how much you're giving any thought to why you're taking this class. Like that's something I should probably do a better job of encouraging you to do. Students should do a better job. Like we get down into the trenches and you're thinking about grades and we're like, we got to do this, we got to do that. It's a very detailed, close up expression. A lot of you are pre-health science, pre-med, pre-vet, pre-dental. A lot of you are bio majors or biotype majors, chemistry majors. Some of you may be med chem. Organic molecules in the modern world are sort of divided equally between, not even equally, I would say. Financially, it's probably mostly bulk chemicals. We pump petroleum out of the ground, we fractionate it, turn it into products, right? The stuff you're writing with and on, most of the clothes you're wearing, a lot of that comes from petroleum somewhere. Like by money, that's the biggest thing. Those are actually really simple reactions. You probably learned most of the ones you need to know in Orgo 1. In Orgo 2, we're starting to, at least at Wake, we tend to lean a little more toward biochemistry, medicinal chemistry, where we look at drugs. So pharmaceuticals that you might take into the body. These are going to be relatively complex organic molecules that have multiple functional groups. Right, so if you think about the way we teach organic chemistry, it's like this functional group, then that functional group, then this functional group. Most molecules have all of them. So this molecule is really pretty simple. It's got 2 carbonyl functional groups and a carbon-carbon double bond. Right, so the big question is selectivity. If we're going to expose a bunch of functional groups to a reagent, ideally, probably what we want is for one of those functional groups to do chemistry and the other one's not to. All right, so it's really too early for you guys to predict this. You almost just have to kind of stick it in your head. Hopefully the blue reaction here going to the right, 1 atmosphere of hydrogen gas, palladium. This is an Orgo 1 reaction, a chapter 7 reaction. And this is going to just hydrogenate the alkene. So I'm going to add agents here. Those 2 agents come from the molecule. So a potential problem would be that you hydrogenate the ketone. So if you let the blue reaction, the hydrogenation reaction, go too long, if you use an excess of hydrogen, like a higher pressure of hydrogen, maybe a higher temperature, it's possible to reduce this ketone with hydrogen gas, but it's easy to avoid, right? You would never really choose to reduce the ketone with hydrogen gas. So the blue product that I drew is, guys, that blue product is going to be what you get. All right. But the reverse is true for the green reaction. Sodium borohydride will reduce the ketone. Sorry for writing small out there. Let me write this lower. So sodium borohydride will reduce the ketone. It will also reduce an aldehyde, but it won't reduce the ester. It won't reduce the carbon-carbon double bond, the alkene. And if you think about this, the alkene is relatively nonpolar. The carbonyl is relatively polar. So we've got a nonpolar reagent that selectively goes after the nonpolar functional group. We've got a polar reagent that selectively goes after the polar functional group. I am recording. All right, so this basically comes into selectivity and its electronics. All right, so for borohydride and hydrogen, we're mostly looking at electronics. We can also look at sterics in that. We'll do that in a second. And I'm going to talk a fair amount about stability.
And all of these differential rate, these are the same thing. Right, selectivity, if I say a reagent, so there are cases where a reagent is 100% selective, like this reagent will not react with that functional group. That's relatively easy in the lab, right? I can just dump in as much of the reagent as I want, I can heat it up, I don't have to worry about it. Most of the time, these selectivities, and it's like this hydrogen gas, right? I can reduce the ketone with hydrogen gas. So I have to be careful there. I have to watch how much I put in, I have to watch the temperature. This is a paper class, a theoretical class. So I'm gonna let you tell me it's selective. In real life, if you actually had to do this reaction, you'd want to watch really carefully. If I did this top reaction, I'd want to watch really carefully for this product. All right. And then if I go in the NMR and I see this product, right, like that C13 signal goes away, that IR stretch goes away, maybe that proton NMR signal shows up. Say, oh, I back off. I do this, I do it shorter, I do it less hydrogen. The other thing in the lab, right? You guys come in the lab on whatever day of the week you come in, you do the experiment once. You follow a recipe that we've worked out. In real life, if you were doing this, say you had 2 grams of this and you need to reduce it, you don't use 2 grams the first go, right? You use like 10 milligrams and you make sure you've got the conditions right. Because if you screw up 10 milligrams, you still have almost 2 grams. If you use the whole thing, you're screwed. Okay, so again on selectivity, lithium aluminum hydride, we've talked about this a fair amount now. Lithium aluminum hydride is a more powerful hydride reducing agent. It's going to produce both carbonyl functional groups. So that would be our product. The red reaction, 2 equivalents of alcohol. Again, this could be 2 moles of alcohol, or it could be 1 molecule with 2 OHs on it. Catalytic acid will make an acetal on the ketone. How many of you drew that product? How many of you did the same thing here? It's a good logical, given how crappy my lecture was at the last bit of Wednesday. I'm sure you've all forgotten that at this point. It's not like I recorded it and put it on the internet. So this all comes to selectivity. And if you look at this, if you look at that whole screen now, it should become apparent. I'm going to ignore the alkene for right now. And the ketone reacts faster than the ester with nucleophiles. Right, so sodium borohydride is a weaker nucleophile than lithium aluminum hydride, so sodium borohydride only reacts with the ketone. Lithium aluminum hydride hits them both. The alcohol, if we make an acetal, we can make an acetal on the ketone, but not the ester. So this is like a general. That's a general thing you want to know. Guess I should put in here aldehydes and ketones. It's actually all on there. How be doing? All right, so aldehydes and ketones react faster with nucleophiles than carboxylic acid derivatives, most carboxylic acid derivatives. This is why they get 2 different chapters. They also are going to react differently. Okay, so aldehydes and ketones are in chapter 19. Carboxylic acid derivatives are in chapter 20. They both have carbonyls, right? So there's a partial positive there, partial positive there. There's two significant differences, all right? Sterics a little bit, not much. A ketone, the two things on, right, the ketone's flat, remember, right? So the two things left and right don't have that big of an influence, you have a little bit. You got kind of the same thing here. By far, the bigger influence here is electronics. So we've got this oxygen that's kicking in some electron density there. So let's think about why that is important. Well, first, I guess I should say this. So aldehydes are generally going to react faster than ketones. And that is more of a steric argument. You got this tiny little hydrogen here, you got a bigger methyl here. So if I want to hit this position, it's easier to do that with the H protecting than with the methyl. So sterics definitely play a role. And you guys at this point know sterics and electronics, right? You know those two words at least. If I ask kind of a short answer kind of question about why does this happen, odds are 90% of the students in the class are going to tell me sterics or electronics at this point. You might be wrong, might make it up. Those are the two things you go to. And I mean, that works out. Sterics and electronics explain a bunch of reactivity. So you should always think about that. If you see a reaction where one atom makes a bond to another atom, don't just see the two written there as two-dimensional, flat, lifeless things, right? Think about what has to happen for those two atoms to physically come in contact. And if to do that, you have to drag a whole giant molecule up against a whole other giant molecule, that's probably going to be slow. If it's one little atom that just has to sort of sneak in by a bunch of other little atoms, that's easy. Okay, so you should always consider sterics. Electronics then, so let's think about ketones versus, let's do an amide now, right? So ketone on the left and amide on the right. So now I'm saying electronics. Sterics are important here too, right? Methyl, that's a wash. This nitrogen with two methyls is basically, all right, so there's a little bit of a steric, there's a little more steric hindrance to hit this amide on the right than there would be the ketone on the left. That's not the biggest, I mean, the difference in reactivity of these two molecules for nucleophiles is like 7 to 8 orders of magnitude. You can easily add a nucleophile to the ketone without adding a nucleophile to that. So what I want you to do now is think about the electronics. To think about electronics, what should you do? Formal charges, draw resonance structures. So draw me resonance structures of those two molecules. All right. So we've done this, we've done the carbonyl before, and again, this should be pretty quick for you now. Carbonyl is very polar. The oxygen's got significant partial negative, the carbon's got significant partial positive. This resonance structure explains a lot of the chemistry of any carbonyl, including the one on the right. So let's just go ahead and do that on the right. We can draw the same resonance structure. Every carbonyl you see, like it's easy. If I say 5 points, draw a resonance structure of this carbonyl, like that should be. I'm giving you 5 points. If you just have to draw one, right? Pop the pi electrons up onto the oxygen. O minus, C plus. There you go. Any others? Right. So the difference here, and again, I didn't draw these in, but you should see these at this point, right? There's also some lone pairs in the oxygen. So you've got that there. Rather than taking the just the pi electrons up, you can take the lone pair in the nitrogen, make a pi bond, kick the pi electrons up, and then this gives us third resonance structure. Here we go. Formal charges are important there. If you draw a resonance structure, you've got to put the formal charges in. There were some points that were lost on exam 1 by not putting in the right formal charges. I've talked to a fair number of people that came in, and there were others who haven't come in to talk about it. And you guys can see, you might see this. If you look at the mechanisms you draw when you're doing homework, on the exam, if you're working with people in Chem Center or on the table, if you screw up the formal charge at the beginning, so you start moving bonds around, but you don't move charges to accommodate that, you'll screw yourself up. And like once you go down, once you do that once, I move a bond, I don't move a charge, I don't put the charges in right, I'm going to miss that problem. So the formal charges are really important. The other thing is, this is a very important, this is like, when I say very important, what I mean is it's a significant contributor to the overall structure of the molecule. So is this one. Like, if you look at the chemistry of any carbonyl compound, the oxygen's a little basic, carbon's a little Lewis acidic. But you don't really see any change here, right? That, like, the carbon is sp2 hybridized in this structure, it's sp2 hybridized there. You can't really see that with the, we can't really see how important that contributor is just by looking at the structure. The carbon-oxygen bond length is still really close to just a carbon-oxygen double bond length. So right, this top structure is more important. For the amide, and for amides in general, that structure where you have the carbon-nitrogen double bond is incredibly important. Okay, so think about amides, why we care about amides. Proteins are made of amide bonds. So they're just amino acids linked together, nitrogen to carboxylic acid. And they have a much more well-defined structure than you would expect just by looking at this Lewis acid or Lewis structure alone. And the other thing is, I think this was probably too late for this, if you can curse my name. You guys made an amide, you iodinated salicylamide in lab. And in the NMR, we would expect that these are magnetically non-equivalent. Right? So if this is a carbon-nitrogen double bond, it's planar. This methyl would be cis to an O minus. This methyl is cis to a methyl. Like that's two very different magnetic environments. And it turns out rotation around that CN bond is slow enough that we don't see it in the NMR. Right? So if you think about the NMR, we put this sample, we suspend the sample in a magnetic field, all the nuclei line up with the field, we pulse it, all the nuclei get excited, we listen for them to relax. That's actually the signal that's being acquired. is listening for these excited nuclei to relax. It takes about a second. Well, for most molecules, like in this molecule rotates around this bond like 600 million times in a second. So what we see is just an average of where these two protons are, right? And on average, those two protons are in the same space, the same magnetic environment. Over here, this molecule rotates around the CN bond like once every 20 or 30 seconds. And so we see the two metals as distinct. So if you're wondering in that Solis Lambda why there were more NH signals than there should have been, that's why. I know at least some of you had a lab instructor not tell you about that. So this does a couple of other things. Right? What do we, when we start doing resonance structures, what do we tell you about them? What do we tell you about a molecule that's got more resonance structures than another? Yeah, so this kind of rule of thumb. It is not a rule of, it's not like, I don't know, curvature of space-time or something, right? It's a good rule of thumb. The more resonance structures you can draw for a molecule, the more stable it is. That doesn't, it means it's more stable. Basically what we mean by that is the more resonance structures you can draw, the more stable it is relative to what you would think it would be from its Lewis structure, right? So for the amide, we get 3 pretty significant resonance structures. For the ketone, we get 2. So at a first approximation, the amide is more stable. So if we now think about reacting with a nucleophile, okay, so if you attack with a nucleophile, right, the tetrahedral intermediate that we get the tetrahedral intermediate we get from nucleophilic attack on the ketone looks really similar to the nucleophilic attack, the structure we get from attacking the amide. When a nucleophile attacks the carbonyl carbon, we get a tetrahedral intermediate. The hybridization of that carbon changes from sp2 to sp3. And all of a sudden, there are no resonance structures to draw. Right? So these are obviously not exactly going to be in the same place. And then they're going to come down to an alcohol. And again, they're not going to come down to exactly the same place because they're different molecules. But the difference between the 2 tetrahedral intermediates that have no resonance and the products which have no resonance is really small. The difference between the starting materials, where you do have this resonance effect, is big. Right? So attack on the amide is slower than attack on the ketone. I'll go through this one more time. I draw these diagrams and I'm like, look there, it's obvious. Sorry for that. All right. So again, what I'm saying here is ketone versus the amide, you've got a significant difference from delocalization of the electrons. Right? So we've got more resonance structure, we have a molecular orbital that's bigger, we got electrons that are down in that. Think back to conjugated dienes and aromaticity. In the ketone or the aldehyde, we don't have that. We have some resonance, right? So the ketone's more stable than you would expect, but not by a lot. The resonance difference between the ketone and the amide is pretty extreme. Once a nucleophile attacks, right? Nucleophile attacks here, kick the pi electrons up on the O. We'll have the nucleophile bonded to the carbon. That carbon's now sp3. So for the ketone, it would be just like another methyl here, right? For the amide, it would be a nitrogen. There's no resonance here. There's no way to delocalize the O-, there's no way to delocalize the electrons on the nucleophile. So whatever difference is there is, some sterics, strength of the bond, the nucleophile that has ends, but that's the same for both things. So like I said, the transition state energy isn't that high. The product, the difference in energies between stabilities between the products isn't that big. The transition state's not that big, but the difference over here is big. So the slow step is slower for the amide than it is for the ketone. That's going to work the same if this nitrogen is an oxygen. It's not as big an effect. Right? So it would be easier to add a nucleophile to an ester than it would be to add to an amide. And we'll talk more about that in chapter 21. 20. Questions about this? All right, so let's come back over to all the reactions you guys did at first. I'm going to erase this, but if you didn't write it down, you want to. Again, the summary of all that explanation was ketones and aldehydes going to react faster with nucleophiles than esters and amides. And that's going to be really important. For one, it's really important here. We made an acetal on the ketone. We didn't do anything to the ester. All right, you have that selectivity anytime you want it. It's actually really hard to make an acetal kind of bond on an ester or an amide carbonyl. All right, so this acetal actually lets us, the reason we would want to do that is it's going to let us do chemistry on the ester without doing any chemistry on the ketone. All right, so let's say you wanted to do this. So I want to reduce the ester without reducing the ketone. There is no way to do that in one step. All right, the ketone reacts to nucleophiles faster than the ester does. So there is no way, you can't just, because I want to, I'm going to reduce the ester, I'm not going to reduce the ketone. Some of you in here will write that down on exam 2 or a quiz or something. I did once. Right? You got 5 minutes to go. I know I got to reduce the ester, so I just tell the professor, yeah, the ester reduced. Say it with confidence. Trouble is, this is not an elevator pitch, right? I'm grading these like in my recliner, comfortable, relaxed. I can think through things. Like you're not going to just blow me away with confidence. So the fact that I confidently wrote down, I'm going to reduce the ester, my professor was like, yeah, no, you're not. So confidently trip on my chair. So here's what you have to do. It sounds like it takes a lot of work, but in synthesis, this happens all the time. This is actually a fundamental piece of organic synthesis. All right, I've got a molecule with like 19 functional groups that all have different reactivities. I need to react one of them. So some of them aren't going to come into play. Like half of them just aren't going to react with the kind of reagents I need for the one I need to react, right? I should probably have a concrete example. But I mean, it would almost be like if I brought in, there's 40 of you and I brought in a piece of coconut pie. Like half of you might just be like, I hate coconut pie. All right, but then how do we figure out who gets the piece, right? So in here, like if I just set it in the middle of the room, half of you wouldn't move. And then it would pretty much come down to a combination of power and aggressiveness, right? Who is closest to it? Sterics, right? Who's trapped between two people who hate coconut? Sterics. Who weighs 240 pounds and wrestles? Right? That's probably electronics if we're doing the analogy, right? So, if the big strong person is sitting right next to it, it's theirs. Right? So what we would have to do if I wanted one person to do it, If I wanted to give it to one of the coconut lovers in the room and not anybody else because I'm a jerk, right? I would have to like find a way to slip it to them. Right? I might tell everybody you have to, nobody can get up, right? Nobody can move. So what you have to do is protect. The analogy starts to fail if you take it too far. So this is really what we're doing here. The whole problem is that the ketone reacts fastest. Right? So out of all those 19 functional groups in my molecule, half of them aren't going to react at all, but the other ones are going to react. They're going to react at different rates. If the one I need to react with reacts fastest and is most sterically accessible, hey, that's no problem. I just do the reaction, right? So if I need to reduce the ketone and not the ester, this is easy, right? I just do sodium borohydride. I use kind of a low intensity reagent. I hit the most reactive functional group, one step. If I need to react a functional group that is less reactive, I can't do it. I can't make the ester more reactive. So what I have to do is take advantage of the fact that the ketone reacts and I protect it. So an acetal, so this functional group, actually, this functional group, actually I've blown the whole thing. Trying to remind you what the functional group is, distracting from the message. That's an ugly looking molecule. So the functional group is two oxygens, not OHs, OCs, two OCs bonded to the same carbon. And if you think about that from last time, this is not an oxidation or a reduction. This carbon right here has two bonds to oxygen. This carbon has two bonds to oxygen. We're changing the hybridization from sp2 to sp3. All right. The other thing, the thing to keep in mind is the acetal is now not reactive to nucleophile. Same thing, right? So acetals do not react to nucleophiles or bases. So I react the more reactive functional group in such a way that it suddenly is not reactive to what I need to react. Right? So then I'm going to do, now I can hit it with the more reactive reagent, right? If I do lithium aluminum hydride the first time, the ketone goes down, right? I reduce the ketone. But an acetal is not going to react with lithium aluminum hydride. So I react with lithium aluminum hydride. The only thing for it to react with is the ester. More on how we, so remember, lithium aluminum hydride will produce an ester all the way to a primary alcohol. The RO part, the RO8, the RO part of the ester will come off as an alcohol. So we'll get ethanol. We get ethanol from this bit. This carbon gets reduced all the way down. We add one H, we kick out OET minus, we get an aldehyde, we add another H there. All right, cool. So I've reduced the ester. I've still got the ketone carbon in the same oxidation state. It's just an acetal. To get to where we want to go, I simply add aqueous acid. All right. So acetals I'll get out of the way. Sorry. Right. So you can make an acetal. It's not going to all fit in. You can make an acetal. You can make an acetal by treating with alcohol and catalytic acid. And then you can hydrolyze the acetal back to the carbonyl by treating with water and acid. All right, we have this equilibrium. Carbonyl plus alcohol, acetal plus water. If I had water, I go the other way. If I had alcohol, I go the other way. That probably would be better as something drawn. Yes. Yeah. Lithium aluminum hydride is sometimes called LAH. Yes. I can't. That's going to be the next thing we. Yeah. Think about that. All right, so I am going to answer your question about why. So it's an important part here. When we add nucleophiles to carboxylic acid derivatives, like an ester, amide, acid chloride, anything that's got a carbonyl bonded to something that's not a C or an H, we're going to add that nucleophile twice. All right, so H goes in, we kick out O minus, that gives us an aldehyde, H adds again. We did that it's been like a week, so, and we're going to go over it again here in just a second. That's an important point. So first, I want you to draw me the product of the Grignard reaction. I've just drawn in green. Weather got cool and with Christmas mode. Sorry. Come block you guys. Yeah.
So the anti-more, why does the ester not turn into like the OH, like the one that was
Because sodium borohydride is not powerful enough to react with it.
So it just says it's a weak.
Yeah, it's a weaker nucleophile. So ketones and aldehydes. All right, I'm going to go ahead and a reminder on Grignards. I've drawn this a few times. I haven't like properly just talked about Grignards much. It's a carbon nucleophile. You guys can picture it being that. Whatever the magnesium is bonded to, or if you see lithium, whatever the lithium is bonded to, you can just treat that carbon as if it's an anion. All right, super strong base, good nucleophile. So that's going to add in. All right, we're going to get an intermediate here. And this is I've used this word a couple of times. It's a tetrahedral intermediate. The product in this case is going to end up being a tetrahedron, but it doesn't always have to be the case, as we'll see in the next reaction. And then, so this is step one. This is the product of step one. And then the H plus, we just pronate the alcohol. product. Right, so these Grignard reactions with carbonyls are pretty simple. Whatever the Grignard is going to add to the carbon of the carbonyl. Pi bond is going to become a lone pair on the oxygen. And then it might diverge from there. But with an aldehyde or a ketone, so this is chapter 19, or no, this is chapter 12. I think it's 12 and 19. Addition of Grignards to an aldehyde or a ketone is pretty straightforward. All right, so let's do. Could have set this here to keep it even, but you could use as much magnesium, you could use as much Grignard on top as you want. On the bottom, I'm going to tell you we have at least 2 equivalents. Just draw me the product of that. So there's the product. So hopefully you added at least 1 phenyl group to the carbonyl. This is actually the reaction you guys did with the Grignard in lab, right? We took methyl carbonate. That's a carbonyl bonded to 2 OR groups. And that one we added 3 equivalents of Grignard. We also took, can't remember what the other ester was, but we reacted with an ester and we added 2. It was like ethyl benzoate, and we added 2 Grignards. So here's what happens. First step is exactly the same as above, and we get a tetrahedral intermediate. Going to put brackets around the intermediates. Right here, the brackets mean this is not isolated. This is not something we isolate. You're rarely going to isolate something that's a really strong base or strong acid. Right, so that O minus is a fairly strong base. So this tetrahedral intermediate is just that. The first step is the nucleophile adds to carbonyl. Sorry, you guys are disadvantaged over here. First step is nucleophile adds to the carbonyl. Electrons go up on the oxygen. But now you have a leaving group. So up here on the top, in the green reaction, what I've drawn is the tetrahedral intermediate. There's no leaving group. O minus isn't going to kick out C minus, right? An unstabilized C minus. That O minus is a strong base for water, but for an organic, like if there's no alcohols or water around, that O minus is a way more stable base than a localized negative charge on C. We do this, I think, in Gen Chem. We certainly do it in Orgo 1. Like compare the base strengths. Hydroxide, like OH minus and CH3 minus. OH minus is way more stable, right? Because the O is more electronegative. So this is irreversible. This step is also irreversible. The O minus isn't going to kick out the phenyl minus, but it can kick out instead another O minus. Right, this is what happened in the lithium aluminum hydride reaction over here with the ester. Right, so the H minus adds in here, we get a tetrahedral intermediate. The O minus kicks out the toxide, sorry, and it remakes the pi bond. So that's kind of the key bit here. That O is going to stay a minus. And in this case, we get a ketone. All right, the ketone, I'm not putting in brackets, it is an intermediate, but in principle, you could isolate that ketone. Right, that ketone is a perfectly stable molecule. It exists, you can buy it, you can make it, there are ways of making it. But in this reaction, we've got a ketone with a Grignard. Right, well, I just spent 45 minutes trying to convince you a ketone is going to react with nucleophiles faster than an ester. Right, so let's say, you know, again, we have a sea of molecules. We have a 10 to the 20th molecules in this flask. We have 10 to the 20th esters. We have 3 or 4 times 10 to the 20th Grignards. Okay, a Grignard adds to the ester. Now we have one in this flask. We have 10 to the 20th esters. We have 10 to the 20th something, 10 to the 20th Grignards. We have one of these and one of those. Right, we have one ketone and we have like 10 to the 20th esters. So this sounds crazy, but the ketone's actually going to react faster than all that sea of ester. Ketone reacts much, much faster than the ester does. And so what happens is the Grignard, we still have, right, we have excess Grignard. So that's going to attack. And now it's, right, this is just adding a Grignard to a ketone. So now our tetrahedral intermediate is irreversible. Or intermediate. And this is the product of step 2. Right? So that last intermediate there is the product of step 2. This thing is the product of, sorry, step 1. Sorry. So that intermediate is the product of step 1. The propyl oxide is the product of step 1. Protonate this, we get an alcohol. Protonate this tetrahedral product, and we get the alcohol. Yeah.
So where exactly, like if you're drawing the mechanism for this, would you do like just both the protonations at the end together?
Yeah. Yeah. So yeah, that it's actually keeping track of when protons are put in there is important. You can't protonate. You can't protonate this anion until step 2. Right? There are no protons available until step 2. So that's just going to hang out as an O minus. So the product of step 1 is both this anion and that anion. Then you add acid, you protonate with them. Yeah.
Why is that propyl oxide more standard than the oxide group?
The methoxide group. What methoxide? It's not. They're roughly equally stable. So you remember delta G equals delta H minus P delta S, that equation? So you've got enthalpy, you've got entropy. Enthalpy for a localized O minus is about the same. So for this reaction, going from this tetrahedral intermediate to the ketone, delta H is basically 0. You've got an O minus, you've got an O minus. So delta H is essentially a wash. One molecule turns into 2 molecules. So entropically, it's driven by entropy, right? It's more disordered. It's a very good question. Yeah, I'm gonna stop there because otherwise I'll talk for an hour. Yeah, so the first step is mostly driven by delta H, right? Because you're taking two molecules, making one. Entropically, that's not favored. You make a carbon-carbon sigma bond in place of a CO pi bond. So delta H drives the first one, delta S, delta H, and then delta H again at the end.
Yeah, I understand, thank you.
Yeah. All right, so here's the thing. Some general rules. If you add a nucleophile to an aldehyde or a ketone, nucleophile is going to add to the pi bond, carbon oxygen pi bond. You're going to get an alcohol. All right. Again, this alcohol can do all the stuff that you know alcohols can do, right? That O can be a weak nucleophile. The O minus can be a strong nucleophile. You can lose water, right? You can do an acid catalyzed dehydration. You can turn it into a tosylate. There's all the stuff alcohols do that alcohol can do. In chapter 20, all right, so if we add a nucleophile to an carboxylic acid derivative, so X here is not equal to carbon or hydrogen. We're not quite there yet. One of the reactions you can do is just a substitution. The nucleophile can just substitute for the X. I could turn an amide into an ester, or an ester into an amide, or an acid chloride into a thioester, right? I can exchange one heteroatom for another. The other thing it can do, which we just did today, is it can add twice. The bottom one is going to be typical of a carbon or a hydrogen nucleophile. So Grignard reagent, hydrides, so the ester over here that gets reduced all the way to a primary alcohol, the Grignard that adds twice, right? So the nucleophile is going to add in, you're going to get an O minus, and it can kick out X. And then it depends how stable that is. So if you make a ketone, the reason the bottom one is typical of C and H nucleophiles is that the intermediate, right? The intermediate is a ketone or an aldehyde. Ketones and aldehydes react again with a nucleophile. Up here, if the nucleophile is right, the nucleophile is not a carbon or a hydrogen, you're going to get another carboxylic acid derivative. And then it might do the bottom reaction, it might do the top reaction. They said we're going to do 13. You guys want me to do chapter 13 in 3 minutes? You wanted 2 minutes, is that? Actually, I'm not sure. Is 3 minutes, do you think 3 minutes is too long or not long enough? Any questions about what we just did? Yeah.
Would it ever happen where
Here?
Yeah. Would that ever?
No, because here's the thing, you can't have a Grignard and protons. So right, this 1 and 2 is really important. If I have any acid source in here, like this is something important to say, right? Like if this were in methanol, say, if I had a Grignard with methanol, that Grignard, before it does anything else, it's gonna take the proton from the methoxide, from the methanol. Okay, methoxide, benzene, nothing's gonna happen. All right. This is sort of an important. I don't know if anybody's at home right now. So proton transfer reactions are usually faster than everything else. By usually in this class, you can basically assume it is. Some of that is delta H, and some of that is just sterics, right? Like the proton's tiny, and it's got the proton, because it only makes one bond, has to be on the outside of the molecule. So a lot of times, if you think back to SN1 and SN2, like the electrophilic carbon might be buried. Carbonyl carbons can get buried. Benzenes can, you can get stuff in both ortho positions. Proton has to be on the outside of the molecule, so it's always sterically accessible. So generally speaking, if a proton transfer can happen, if you look at it and you're like, oh, there's an acid base here, they can do something. And you think there's something else that might happen. That something else isn't happening, right? Because the proton transfer is going to happen fast. So these Grignards and the LAH. So it's worth keeping this in mind. If you have a Grignard or an organolithium or lithium aluminum hydride, you cannot have alcohol or water. Keep talking. Any more questions? I'm just going to pass these out real quick. I want you sort of didn't go where. Here you go. Didn't really go where I thought it was going to go. So please put your name on that, fill in the answers as best you can, then bring them up, drop them off. Read, if you haven't yet, read chapter 13. Before class on Wednesday. Yeah. Yeah, there's a really good question here. Do you ever have to indicate chirality here? And the answer is no, for a couple of reasons. Up here on this top one, right? If you look at the addition to the ketone, the product is chiral, right? You got a carbon here with 4 different groups on it. The nucleophile is attacking. The nucleophile is achiral. The reactant is achiral. So the product has to be racemic. You can also see that nucleophile can lay down on top, it can lay down from the bottom, doesn't matter, it's going to be here. The same is true of this tetrahedral intermediate, but it doesn't matter because 1, it's going to be racemic, and 2, you're going to kill the stereochemistry anyway, right? So when I kick out the OR group, now I'm not chiral anymore. And because I'm adding the same nucleophile twice, that carbon isn't going to be chiral. Right, so the product over here has 2 phenyl groups on it. That carbon is not chiral.
So would you want us to write racemic?
No, it's not a terrible habit to get into to write racemic or plus an enantiomer. But no, if I ask for the product of that and you draw that, unless you write in there like 100% EE or 91% EE or something, I'm going to assume it's racemic. Yeah. If I care, I'll ask you explicitly, like, what is the EE?